class we were discussing the determination of crystal structures in case of simple crystals like from the cubic space lattices. It is easy to do that, and we said that for using that we normally can use X-rays, neutrons or electrons, and X-rays what we use are the characteristic radiations of some of these targets which I told you yesterday. Then we also looked at the Bragg law which we exploit in trying to determine the Miller indices of the planes which are diffracting, X-rays which are incident on the crystal. Worked it out, n lambda is equal to 2d sin theta, where n we discussed is the order of diffraction. We said that we will take it to be 1 because otherwise it is not possible to distinguish first order from one plane and the second order from the another plane which are superimposed. In the camera which we use for the powder method, generally how we measure the theta values, I described that this is the incident ray of X-rays. This is directly transmitted out from the camera. These are the diffracted rays which form a cone from the specimen which is somewhere here in the center of the camera. The angle which is formed here between the incident ray and the diffracted ray is 2 theta. Similarly, this angle is also 2 theta. And if I am able to measure the distance between these 2 points or the length of this arc, which is, let us say, is S, divided by R becomes 4 theta. That is the angle. That is how it is possible for us to measure the angles of diffraction. Similarly, if we are using a diffractometer, only the lower half of the geometry is required, then I am directly measuring with the help of the Geiger counter the 2 theta angle for diffraction, and from there again I know the value of theta. Then in cubic crystals we also saw that the sum of the squares of the Miller indices of the planes which are diffracting h square plus k square plus l square is directly proportional to sin square theta, and since we have measured theta values, I know their ratios, sin square theta ratios, therefore I know the ratios of h square plus k square plus l square values which we observe. And what is the first value will give me all the subsequent values, that is given by the extinction rule. Extinction rules say that in a particular crystal like simple cubic, what values of h square plus k square plus l square are observed. In this case all of them are observed, 1, 2, 3, 4, 5, 6, of course 7 is not there. You know the reason, there are no 3 integers the squares of which are summed up to give you 7. Okay, like that there is going to be 15, there is going to be 23, and so on and so forth. Similarly, in body centered cubic crystals we have it is all even values of h square plus k square plus l square. Well, as I have repeated yesterday, again I repeat this, that 2, 4, 6, 8 again becomes 1, 2, 3, 4, but the difference comes when we look at the 7th. Here it is 14, but there is no 7 here. Okay. Like that we discuss these extinction rules for FCC and diamond cubic. I will just give you an example here why we do not see certain h square plus k square plus l square values. Let us consider this to be a BCC unit cell, and here I am looking at the diffraction from 100 which satisfies the condition lambda is equal to 2d sin theta, and this is my angle theta here, and that is another angle theta there. At the same time in BCC I also have an interleaving plane which is called 200. When this is satisfying Bragg law as the first order, that means the path difference between this ray and this ray is 1 lambda. That is the meaning of first order, right? The two consecutive 100 plane give the diffracted ray, the path difference is 1 lambda. Now this 200 plane sitting in middle also form the same angle theta, and the diffracted ray here from here to there is path difference is only lambda by 2. These are completely out of phase when this condition is satisfied. So when this is satisfied, I should see the diffraction from 100, but because of the 200 sitting in between, physically sitting there, I cannot see that because that gives me completely out of phase. There is total cancellation of intensities. Okay.
Intensity from 200 will also cancel, but
intensity will be exactly same as long as this is BCC, means the atom sitting there and the atom sitting in the body center is exactly the same. Number of atoms per unit area, the scattering centers is the same here. Is also one in this area, this is also one in that area. So from the given plane, the number of scattering centers are exactly identical. Number of electrons on the outer orbits of the nucleus is the same because it's the same atom. However, the atoms are different, amplitudes may not be same because scattering centers are different then. But here identical scattering centers with equal number sitting per unit area, therefore I get this same intensity, same amplitude. Only thing is it is out of phase.
And both cancel each other.
Both cancel each other completely. So that is why we call it extinguished. It is not that the Bragg law is not satisfied. Bragg law is satisfied for the first order from 100, but it gets extinguished. That's why I call it extinction rules.
So then first order from 200 also get extinguished now?
No, when I say first order from 200, the path difference between these two consecutive rays instead of lambda by 2 is lambda. Once that happens, this becomes second order from 100. That's why we call it 200. See, the meaning of first order is the given plane HKL said the path difference of the diffracted rays coming from the two consecutive planes is 1 lambda. That's the meaning of the order of diffraction which I explained yesterday. This is what it is. Is that clear? Right.
Lambda by 2 implies it is second order. The path difference.
It's not implying, it's saying this is path difference is lambda by 2, it is out of phase.
It is second order.
It is out of, it will become second order when only the path difference here is lambda. Then the theta would be different. That condition would be different. That would be, this is D100, that would be lambda is equal to 2D200 sine theta. That would be satisfied. Again, this would be the first order from 200, but when I rewrite this, it becomes second order from 100. Is that clear? Why we don't see 100 in body centered cube? Right. With this, it is possible now, therefore, for us to determine the simple crystal structure where there is only one atom sitting on the lattice point and it is a cubic crystal. Now we shall look at the structure of solid materials, and today we shall try to look at the covalently bonded solids. Solids could be having basically by and large covalent bonding, or they could have metallic bonding, or they could have ionic bonding. Well, you have studied this in chemistry, but you have also seen that no system or no two bonds or no bond in particular is 100% covalent or 100% ionic or 100% metallic. This is for the simple reason electrons are not stationary. They keep orbiting around the nucleus, and thereby if there is most of the time spent sharing there together in the same orbit, it is covalent. If they spend most of the time only on one atom, it is ionic. If they are shared equally between all the atoms in the solid, it could be metallic. So it depends how much time they are spending in which form. We name them as covalently bonded or ionically bonded or metallically bonded. Today we shall first, as I said, look at the covalently bonded solids. Now, before I look at that, the stacking in the solid can be seen in two ways. One, what is the local or short range arrangement around a central sphere or central atom. I am calling sometimes sphere, sometimes atom, because I have already said we will consider all atoms to be hard spheres. Around the central atom or central sphere, how the neighbors are arranged, that is why it called the local arrangement. This is by and large dictated by the nature of the bond between the two atoms, right. Then this local arrangements have to continue in 3 dimensions. Whether it can continue in a repeating manner or it cannot, I get a 3-dimensional crystal which is crystalline or non-crystalline. If it repeats in a periodic manner, it is crystalline. If it doesn't, it is non-crystalline, right. So that is the 3-dimensional or long range arrangement is what shall dictate whether it is crystalline or not. As I just said, the solids are covalently bonded, metallically bonded, ionically bonded. When they are covalently bonded, the sharing of electrons occurs, and these are localized sharing. We also find in such many of such solids, there are other kinds of bond present in the system which are weak bonds, van der Waals forces or hydrogen bridges. When there are two kinds of bonds, one primary like a covalent bond, or the other one which is a physical or a secondary bond like van der Waals force or a hydrogen bridge, properties of the material will be dictated by the weaker one. Weaker one are the van der Waals forces and the hydrogen bridges, right. We will see that there are many of such solids which are there. Then we shall look at long range arrangement, which is many times we find in metallic and ionic crystals. There it is possible to see the long range arrangement. First of all, we shall look at the periodic table, we shall look at the elements, and instead of going from group 1, I start from group 8. In group 8, around the nucleus, each atom or sphere has 8 electrons in the outermost orbit. Its octet is complete, it is satisfied. That means what we call the octet rule. Octet is complete, it has no tendency to form bond with any neighbor, and thereby there are only van der Waals forces between them which are non-directional in nature. When I have non-directional nature of the bond in 3 dimensions, the atoms will come from all possible directions around a central sphere. How the central localized arrangement occurs and how it goes on to the long range, we shall see when we are talking about the metallically bonded crystals, because there the bonds are also non-directional in nature, and central sphere likes to have the neighbors from all possible directions. That we shall see with that. Coming to the group 7, where we have halogens, fluorine, chlorine, bromine, iodine. There are 7 electrons in the outermost orbit, one is shared with the neighbor and a molecule is formed. There is a very strong bond between fluorine, fluorine, very strong bond between chlorine, chlorine, it is a covalent bond. But between the 2 chlorine molecules there are van der Waals forces. Again there is a non-directional nature of the bond, and non-directional bonds, the weaker bonds, are very long as compared to the primary covalent bond, and they are also non-directional. So here I have shown the orthorhombic unit cell of bromine, which could be chlorine. These are the spheres here. The white ones are on the front plane, front face. This is in the center, face center. These are in the corners in the bottom. Those black ones are the back face, and these grey ones are in the middle faces, right? And this is also the face center. You see the top face and the bottom face, their arrangement looks similar, they are oriented in this direction. With the middle face, they are oriented opposite, means this is gone mirror image.
In this game, motive is to. What?
Pardon?
So what is the motive in this?
I'll come to that. Just wait, just wait. We'll, if you want to talk about motive, we'll talk about that. So this, what I am trying to say is, between the molecules, there is a long distance, and this is a van der Waals force between them. At very low temperatures, they can condense like this. This is a very short distance, and this is a covalent bond between chlorine, chlorine, or fluorine, fluorine, right? Right. These dimensions of the unit cell will be large as compared to this bond length, very large. Now, my friend is asking what this space, if it is an orthorhombic, what is going to be the space lattice? Then we shall look at the motif. What would be a space lattice where this is arranged in this orientation to the right, tilted to the right, and this is a mirror image tilted to the left on the middle faces. So, if you take this 100 plane, top and bottom is identical, the 200 plane orientation is different. What should be the name of the space lattice for such a cell? How will you name it? Pardon? Somebody said something. End-centered orthorhombic. It's not face-centered orthorhombic. Why is it not face-centered? This arrangement is not identical to the corners. That's not identical. So these one in the middle plane are not the lattice points. Those are the lattice points, and those are the lattice points. And you see now, in all, if you look at this, there are 4 molecules in this volume, but there are only 2 lattice points. Therefore, there are 2 molecules on each lattice point. So basis would have one molecule here and another molecule there. That's going to form the basis, and that you will find to be same everywhere. Similarly, for this you will find there. For this one you find it here, right? So, and for the one which is here, this is the one, and this face center there, that will form the basis. So these are the problems you have to understand after you have understood what the space lattice is. Each lattice point is having identical surroundings, and then after substituting that, you see what is it left out on each lattice point. That will become your motif. That clear? All right, that's group 7, and these are most of the times we are using them as chlorine and fluorine are gases, but bromine could be liquid, and iodine could be solid, close to room temperature. Now, elements from group 6, there are 6 electrons in the outermost orbit. To complete the octet, they have to share 2 electrons. There are 3 orbits are px, py, pz, and there are 6 electrons. Which will be px, py, pz have only 4 electrons, 2 are gone into the s, and therefore 2 of them share, either px, py share or py, pz share. That means 2 of the p orbitals are shared, and p orbitals normally are at 90 degrees, and therefore we find that group 6 elements form a chain at zigzag chain at 90 degrees, like is shown here. One atom forming one bond with one neighbor, the second bond, this one forms with the second neighbor here, and the bond angle between this is 90 degrees. Similarly, this forms one bond here, another one here, this angle is 90 degrees. This one forms a bond there and a bond there, this angle is 90 degrees. And this zigzag chain has been arranged around a triangular prism. Each atom is on the edge of the triangular prism, but the angles are maintained at 90 degrees when the crystalline arrangement takes place. But between the chains there cannot be primary bonds like we have here. These primary bonds have satisfied the octet, right. So, these are arranged in a hexagonal manner here, these triangular prisms, but between the prisms or between the chains there are only secondary bonds, the van der Waals forces. So, distances between them are very large as compared to the dimensions of this triangular prism or the bond length here, there are much larger distances here. That is what you find sulfur, selenium, etc., some allotropic forms crystallizing in this manner. Right. Again, these are the elements not very much used by as bulk material in engineering. We go to the group 5 elements. Now there are shortage of 3 electrons. So each px, py, pz can share, and this is 90 degrees. When they share at 90 degrees like that, the sharing does not form a sheet. I mean, it does form a sheet, but that sheet is not a plane sheet. Like I show it here, this atom here is bonded to this one, second and the third here, and similarly this one is bonded, one already there, second here and third here. All these angles are 90 degrees, that is what you have to check. Then this is bonded to 3, 1 here, second there, third here. This one is bonded to 3, 1 there, second here and third here. So this is forming a sheet, but the sheet has a certain thickness. Some are projected out, some are projected below the sheet, thin sheet. Okay. So that is how these sheets are arranged. Then there is a second sheet here, then there is a third sheet here, then there is a fourth sheet there. But between the sheets there is no sharing of electrons, and therefore there are only van der Waals forces between them. Again, between the sheet there is a large distance, and these sheets are not plain sheets, these are called puckered sheets. Okay. Such elements, antimony, bismuth, etc., which are there in group 5, we do use them as engineers, and they are very helpful in type casting. Reason for that is very simple. When the melting of such a crystal occurs, it is the van der Waals forces which are going to give way, because this is the weaker one. Once that happens, these sheets collapse and start translating one over the other. The van der Waals forces are gone, so they start translating one over the other. That is the liquid state. As a result, the volume in the liquid state is lower than the volume in the solid state. So once these kind of solids crystallize or solidify from the melt, the volume expands. That is why they are useful in type casting. So for example, I want to make a type like you have seen the typewriters or the computers. Of course, these days we have all the laser printers. I want to make a shape like this. What is this? Digit 1 on the type, right? This is a sharp corner here, these are the sharp corners there. When I fill in a cavity like this, liquid metal, because of the surface tension, it does not fill the whole of it. Liquid gets filled in, but there is a space in which it does not go in. like this, alright, rest of it can fill. So, when it solidifies, this liquid has to expand now in the solid state, metal has to expand, and this will fill this space. You get the corners, very sharp corners are possible to get. That is why they are used in typecasting. Okay. These elements are used in those alloys. Now, from group 5 we can move into the group 4. We shall talk about the carbon first. Carbon has two allotropic forms, one is diamond, another is graphite. First of all, we shall look at the graphite form. There here now we have 4 electrons in the outermost orbit, and to share it has need to share with 4, but outer orbits px, py, pz there are only 3. So, therefore, to share with 4, 2 s electrons and 2 p electrons hybridize to form sp3, that is the diamond, but when they hybridize to give me only sp2 and the 4th electron remains free, it gives me graphite. sp2 hybridization means there are only 3 neighbors equally oriented in space. 3 neighbors equally oriented in space, you will find that it will be in a plane at 120 degrees to each other, and that is what it is. If you look at this one, bonded to that neighbor at 120 degrees, bonded to this neighbor at 120 degrees, bonded to that neighbor. These 3 bonds at 120 degrees to each other. Like this we form the plane sheets now. These are not the as compared to group 5 they are different, these are plane sheets, but again between the sheets there are van der Waals forces only, because that 4th electron does not take part in bonding at all. It remains free to move about in the sheet, and as a result causes the van der Waals forces between these sheets. The distance between them is much larger than the bond length between the carbon-carbon bond length is much shorter than the distance between the sheet. Alternate sheets, or rather the consecutive sheets, are displaced by the one bond length. This is the bond length, it is displaced by that bond length, okay, like that, it's backward, it's gone. So, therefore, it is all displaced by one bond length, and you can take any one of the 3. It is so symmetrical, you can take the displacement around any one of the 3, it will be the same situation or the same story, right. So, the alternate sheets, therefore, after 2 displacements it comes out to be exactly same. So, it forms a hexagonal unit cell. I have shown only half the hexagonal unit cell here, other half is to be extended out, and this forms a graphite crystal which is hexagonal in nature. Between the sheets being the secondary bonds, it gives very interesting characteristics to graphite. The plane sheets with very weak bonds between them, it is easy for them to slide like this. If there is a strong bond between them, it is not so easy to slide, but if it is a weak bond, it is easy to slide. So, this is a very soft material, sheet slides one over the other easily, and we use it in lubrication. In bearings we use it as dry lubricant, use it as bushes, because the free electron which is present in the sheet, it can conduct electricity. We use it as bushes in motors, right. This is also used as heating element. Only thing is, in the atmospheric oxygen it can easily react to form carbon monoxide and carbon dioxide. So, we have to keep it, maintain this in a inert atmosphere, or we have to maintain it in vacuum so that we can use this as a heating element. Well, if you look at the sp2 bond, it is very strong. As a result, any direction on the sheet which has only sp2 bonds is very strong. So, if you try to stretch it with a force parallel to the sheet, act as very strong. But if you apply a force in any direction which is perpendicular or not perpendicular to the sheet, but not on the sheet, it behaves in a very weak manner, because the van der Waals forces are very weak. It is possible for us to make fibers. The axis of the fiber lies on the sheet. So, whenever there is a fiber, the force, whatever way the force is coming, it is coming in the axis of the fiber, because other than 2 dimensions are very small in the fiber, and therefore it acts very strong fiber. The strength of this fiber is very, very high. So, carbon fibers you must have heard of. It's because of that, because only sp2 bonds are there. And this is the use of graphite as lubricant, graphite as a conductor is very much used by engineers. Well, the pencils you use are also having graphite, though we call it lead, but this is not lead. The lead of the pencil is nothing but graphite, but this has different hardness values, starts from 4B, can go up to 4H. 4B may be very, very soft, is almost pure graphite, and then we mix clay in it as a binder, and then it becomes 3B, 2B, B, HB, H, 2H, more and more clay, becomes more and more hard, and then it will not be possible for these sheets to slip, and it will not leave a mark on the paper when it is like 4H or 6H, it will be very, very hard. Now we come to the second form of carbon, which is diamond. Here I have shown the unit cell. We will come back to this unit cell again, but before we come back to the unit cell, we have to see what the local packing is and how do we get the long range arrangement. In diamond form, there is sp3 bonding. S and P, all 3 orbits electrons are hybridized, there is no distinction, and they form 4 orbitals which are equally oriented in space again. Like in sp2 there were 3 orbitals equally oriented in space, now I have 4. And we know that we have seen this in the chemistry, this is also called it tetrahedral bonds. They form a tetrahedron. I have shown a tetrahedron here inscribed in a cube. This is the front top corner, this is the front bottom right corner, this is the back left corner, and this is the back top right corner. This is the center, body center of the cube. This one is equally oriented in space with reference to these 4 corners, which in a cube I have taken alternate ones. This one, leave out that one, next one, leave out this one, take that one, leave out this one, take that one, again leave out that, come back to this. So, alternate corners I have taken. Body center is equally oriented to the 8 corners of the cube. I have taken alternate corners, so it is also equally oriented to these 4 corners, and I can inscribe a tetrahedron inside. Well, the fourth of the side of the tetrahedron probably is to be here at the back. That's the back. This is
Like the face of it.
pardon,
The one atom which is
this one,
no sir.
this one
Yes sir.
is the body center of the cube. This is the body center of the cube. That's why it's bonded to this diagonal. This is a body diagonal, half the body diagonal. This is also half the body diagonal. That's also half the body diagonal. This is also half the body diagonal. These are the tetrahedral angles. You see, this one, this one, this one. These are all tetrahedral angles. Well, yeah, this one is also tetrahedral angle. 4 corners and 4 angles there. They are all tetrahedral angles which are formed, and the angle you know is 109.5 degrees. This is the basic unit I have in sp3 bonding. This is the short range arrangement. I have to see whether I can arrange this in the long range to get a crystalline arrangement, or it will not give me long crystalline arrangement. I have now removed that tetrahedron drawing. This is the initial cube which I have, these 4 alternate corners, and this is the body center. Alright. Now I put next to it another cube which is identical in size. Can I repeat whatever arrangement is here in this position? If I repeat, this sphere goes there. Once I have that sphere here, this is at the same distance from this body center. So, this body center will have more than 4 neighbors, more than 4 bonds. That is not possible. So, it cannot go there. So, I have to leave it vacant. So, this cube is left vacant. Then you make third cube here. So, this is translated from here to there. Similarly, this is translated from here to there. This will be translated from here to the next here. I have just shown the 2, and therefore, this will not be translated to this body center location, be translated to another body center location. So, in other words, I can say that I have a cube with a tetrahedron and a body center inside, but neighboring cube has a tetrahedron in these corners, but does not have a body center. The moment I have that, this will not have its 4 bonds, it will have more than 4 bonds, and I do not want any one of them to have more than 4 bonds, because it is sp3 hybridization in all 3 dimensions. Whether I look at this atom or I look at this atom, all of them should have the same story to tell me. Therefore, this has to be left vacant. Like that, I can put 2 more. Let us see what happens when I do that. These 2 I have made slightly differently. The first one is the one which is empty, and the second one is the one which is going to have. So, this second one is actually my first one, because I use that corner, this corner, this corner, and this corner. In other words, you can say earlier I had extended to the right, now I have extended to the left. To the left of this also will be empty, and this pair and the previous pair which I showed, let us join them. The first one is at the back, and the second one is in the front. Okay. The first one at the back has this as the body center. First one at the back has this as the body center, and the second one here in the front right has this as the body center. It looks as if I am putting at the corner, it is not. I actually worked out the body center, it is slightly displaced from there, like it is slightly displaced from there. So, this is the body center of the front cube which is here on the right. Okay. So, this is a tetrahedron, that is a tetrahedron, but this is empty and that one is also empty in the middle. like this we can construct 4 on top of it, but again we will have to displace. If there is a body center there, the one on top will not have the body center, but here there is no body center, the top on this will have the body center, right. So, like that you can build it again. That shall be the one repeating unit, because the repeating distance is this.
So the unit cell for diamond is this one.
This is half the, so I want to show the inside, so this is half. Other half will have to build on top of it. Like I put 4 cubes here, I have to put 4 more cubes like that. Each cube is only 1/8 of the total unit cell, okay, in volume, right. Let us see the next one. Come back to the first figure which I said. See, what I have shown here is, this is the unit cell. That is the unit cell. Of course, these are the now you see the atoms have come at the 8 corners of the unit cell. Atoms have also come at the top face center, the bottom face center, the right face center, the left face center, the front face center and the back face center there. Then one has come here on the body center of the smaller cube here, top in front. You see, if I divide them, this is the cube which I was trying to show you. Recall that? This is what I was trying to show you. This one, that one I showed you the first one, this one and second one. Well, this is actually, that smaller cube is this, and this is the body center of the bigger cube, this one, this corner, and there is nothing there, and there is one here, the next one is empty, but then when you go at the back there is one in the body center there, the back one. Similarly, when I come below this, there is one in the body center here, and when I go the back of this front one here on the left, this is one in the body center there. And this is how I have 8 corners, 6 face centers and 4 within the cube. This one, this one, this one and that one. These are 4 within the cube. These are within the cube. If you look at carefully, this one starts from here, goes along the body diagonal, which is here. This one starts from here, goes along the body diagonal, which one there? I have not drawn the body diagonal very well. And there is one here, which is on this body diagonal, that is the one. And the fourth body diagonal starts from here, goes up to there, and that is the one on that. So, these 4 which are inside, they are on the 4 body diagonals of the cube. They are within the volume of the unit cell. This can repeat in 3 dimensions and give me the diamond crystal. It's a 3-dimensional long range arrangement is possible now. This is a crystalline arrangement in diamond. Now, there are no secondary bonds anywhere. This is a part of a tetrahedron here, which becomes a part of another tetrahedron there. It becomes a part of another tetrahedron here. This becomes a part of this tetrahedron and becomes a part of tetrahedron elsewhere. So, each one is in the body center of a tetrahedron. At the same time, it is also a corner of the tetrahedron. So, each one is bonded to 4 neighbors, each one, alright. So that goes on in 3 dimensions. As a result, I have only sp3 bonds in all the 3 dimensions. I do not have any secondary bonds anywhere. This is a hardest known material in the world. There is no secondary bonds anywhere. So the fluorine-fluorine bond is very strong, but between the fluorine molecules there are secondary bonds. Van der Waals force is very soft. It's gas, as a matter of fact, at room temperature. This is a solid crystalline material and the hardest known material, because there are no secondary bonds. Group 7 also has secondary bonds, group 6 has secondary bonds, group 5 has secondary bonds, group 8 anyway has only secondary bonds. So this is the first one, and as all covalent bonds in 3 dimensions. Because of this very hard nature of this material, it is used by engineers for, alright, we'll come to that. I think that there's a slide for that. The applications and properties we shall look into, because it's a very hard material. Before we proceed further, this is a crystalline arrangement where I have all covalent bonds in 3 dimensions. We have seen that when I stacked one cube after the next one, each in alternate one is not having a body center and the alternate one is having a body center. That means there is space for that atom to come and sit there. I mean, there is a lot of space there for more atoms to sit, but they are not sitting because they have to maintain sp3 bonding. That means the space which is available to me is not being utilized in a very efficient manner. That we refer to as packing efficiency or atomic packing factor. Either sometimes we call it packing efficiency of the crystal, or we call it the atomic packing factor. That should be very small for this, because there is a lot of open space available, and it is defined as volume of the sphere, because I have considered atoms to be hard spheres. So, or volume of atoms or spheres in unit cell divided by volume of the unit cell. This volume of the spheres will depend upon number of spheres into sphere is sphere 4 upon 3 pi r cube divided by the volume of this side of the cube is A, it is A cube. Now first of all we shall look at this number of spheres, then we shall look the relationship if there is in between R and A to simplify this. In the unit cell of a diamond cube, we have seen there are corner atoms. How many of them are there? 8. Each one is shared 8 unit cells. So I have 1. How many face centered atoms do I have? 6. Very good. And faces are common between 2 unit cells. So it is only 3 in the volume of the unit cell. How many body diagonals and spheres on them? 4. Each one has only 1. Okay. I have 4 body diagonals and each one has only 1. That makes it 4. Total number is how much? 8. In the unit cell, total number of spheres we have is 8. Now let us look, we have defined the diameter of the sphere as the closest distance of approach or the bond length. What is the bond length here? One atom sitting at the corner, other sitting at the body center or the center of the tetrahedron. root 3a by 2, not true, it's root 3a by 4. On this diagonal, I have one here, which is a part of or body center of this cube only. This is the body center, but there is no atom there. So it is this distance, which is equal to 2r. Yeah, 2r is equal to root 3a by 4. Very good. So in other words, r is root 3a by 8, or you can also rewrite this as a is equal to 8r by under root 3. All right, let's go back to what we wrote, the packing efficiency. I wrote the packing efficiency as number of spheres, which is 8, times the volume of these spheres divided by a cube. Now let us substitute one in terms of the other. Yes, what did we say? Root 3 a by 8 whole cube divided by a cube. Now it is possible for me to cancel a cube with this a cube here, because there is a cube there, and if I simplify this, what I get is 8 times 4 under root 3 cube is 3 under root 3. In the denominator I have 3 and cube of 8, 8 into 8 into 8. 8 cancels with this 8, 4 simplifies it to 2, 3 cancels with this 3, and there is also a pi there. So it becomes under root 3 pi by 16. Under root 3 is 1.73, pi is about 3.1, that is product becomes how much? Roughly 5.4 or something, divided by 16. How much it is going to be? Yeah, it will be approximately, alright, let us write it here, 0.34. That means 34% of the volume is occupied by the spheres and 66% is not occupied. We call it vacant space, but this is vacant space is what? Is it vacuum? Is it air? Is it oxygen? What is it? This is vacant space.
Orbital.
Yeah. You are right when you talk about orbitals. They are electrons, but probability of finding electrons in those spaces is very small. Probability of finding those electrons in those spaces is very, very small, right? Therefore, this is simply a vacant space is not, there is no air there, there is, right? And you don't refer it to as vacuum either. Only electron clouds, which there is a probability of finding the is very small. Similarly, you can define the density. In here you need the mass of the spheres. So what will you do? You will write the number again, which is 8, write the atomic mass of carbon, and then volume of the unit cell. It is possible for us to relate the density to the packing efficiency. Okay. Now coming to the properties and applications of diamond cubic solids, as I said already, it is a very hard material. So engineers exploit them in such applications where we need very hard material, like cutting, machining. So you have cutting, abrasion, polishing, grinding. You can make the dies, tools, etc. Otherwise, common man has a jewelry application for diamonds. Right? Besides the diamond, there are crystals which also form in a similar kind of arrangement as with sp3 bonding, but they do not have only one kind of atom, they may have two kind of atoms, and those are called the 50-50 compounds. Say for example, 4,4 is a silicon carbon, silicon carbide. Silicon carbide acts as a semiconducting material till up to about 700 odd degrees centigrade. Beyond that, it becomes something like metallic. So we exploit it as a heating element. Group 3,5 compounds like group 3 is, let us say, aluminum. Group 5, let us say, phosphorus, or the gallium, arsenic. These are semiconducting materials and important semiconducting materials. Then 2,6 similarly are also semiconducting materials, cadmium telluride, cadmium sulfide, zinc sulfide, etc. And similarly 1 and 7 are silver halides like silver iodide. In here what is happening is the face centered cubic locations, which are the corners and the face centers, are occupied by one atom, whether it is aluminum or phosphorus. The body diagonal positions, where 4 within the unit cell, those are occupied by the other kind of atom. So the ratio is 50-50. We have seen that body corners give me 1, face centers give me 3, so makes it 4. The one which are 4 on the body diagonals, they make 4. So 4 and 4 becomes 50-50, right. So that's how these structures look like, and when these elements are diffracted and X-ray diffraction is seen, though I talked about yesterday, diamond cube extinguishes some more lines, diffraction lines from the FCC. They will show all FCC because scattering centers are not identical. Though they are out of phase, but there is no total cancellation of intensities. Those intensities will turn out to be weaker here, but they will be there. Is that clear? That also answers the question which you are trying to ask in the morning. Alright, thank you. We shall start from here in the next class.